Hello chemists, this video is just going to give you a brief introduction to aromatic chemistry, cover a few of the properties and a few of the reactions that you're going to need to know for our first year modules and beyond. So why are we looking at aromatic chemistry? Well, aromatic motifs are prevalent throughout nature. They're found in lots and lots of molecules, whether they're natural or synthetic, and they have a range of different applications. So you can see lots of different aromatic moieties in these molecules. So it's really important to understand how they behave and how they react. So we'll start with one of the simplest, benzene, and a little bit of history of benzene because it's important to understanding the structure and how everything works. So it was well known that the empirical formula for benzene was CH, in other words, same number of carbons as hydrogens. And August Kekule established that the molecular formula was C6H6. What happened then was basically people really struggled to explain the structure, and it was based on how benzene behaved in its reactivity, which we'll come on to in a second. So we ended up with a lot of very, very strange type of molecular structures here, which had to, incorporate some interesting new uses of different types of nomenclature. But eventually, Kathleen Lonsdale was a crystallographer who proved that it was a flat hexagon in 1929. So the Kekule structure was sort of proposed, this six-membered ring with alternating double and single bonds. But there's some problems with this. Okay, so if benzene is a six-membered ring with alternating single and double bonds, it certainly doesn't behave as though it is. And there's a few things that we want to go through here to show that. So first of all, alkenes, double bonds, react with bromine. This is a classic chemical test. We don't really use it anymore because we've got spectroscopy now, but there used to be the test for alkenes, which is that you would shake the molecule with bromine water. The bromine would react with the alkene to dibrominate it. Bromine is orange or sort of deep red in color, and if it's reacted with the alkene to form the alkyl halide, then it's obviously no longer orange. So you would go from orange to colorless, and that is a positive chemical test for an alkene. If you shake bromine water with benzene, nothing happens. So benzene behaves like it doesn't contain an alkene group, which is because it doesn't. Another thing that we noticed about benzene is if you take the enthalpy change of hydrogenation, so various alkenes being hydrogenated down to the level of cyclohexane. So cyclohexene down to cyclohexane has a certain enthalpy change for that hydrogenation reaction, so the energy that's released when that double bond is hydrogenated. If you have cyclohexadiene, you would expect the delta H to be almost exactly twice as big because you're hydrogenating two alkenes, right? And that makes sense. So surely for benzene, you would expect the delta H to be 3 times as big because you're hydrogenating 3 alkenes, but it isn't. Benzene's energy level is substantially lower than you would expect it to be for the structure of cyclohexatriene. So there is something that's making benzene much more stable than we would expect for that isolated structure. Finally, we would also expect the bond lengths in Kekule's structure of benzene to alternate. So typically a carbon-carbon single bond is about 1.5 angstroms, and a carbon-carbon double bond is much shorter, about 1.3 angstroms. So you'd expect to get this sort of distorted hexagon with weird bond angles going all around it. However, the bond angles in benzene are actually all the same. They're all exactly 1.4 angstroms. So something isn't quite right. And we sort of figured out that the Kekule structure can't be the whole picture. And Thiel actually proposed that there was something unusual going on and proposed that there was a sort of delocalized set of electrons throughout the ring. And that's what we now understand is what's going on. So this is this resonance picture of benzene. So if you draw a Kekule structure like this, you can push the pi electrons around in a circle, okay, from here to here to here, and you will end up with a different structure, which is a resonance form of the same compound. Now, you may look at this arrow and go, that's a reaction arrow. That's wrong. You're right. It's about to get corrected. So in this resonance form over here, we can push the double bonds around in a circle again, and we get back to the original structure. And these two structures are resonance forms of the same compound. So the actual structure of benzene is essentially the average of these two. So if we were to take one Kekule structure and the other one and bounce them back and forth very, very quickly, then that's essentially what benzene is doing. Okay, so it's averaging out the positions of its double bonds in this kind of resonance stabilized format. And we quite often, at a sort of A-level standard, draw this as the six-membered ring with the circle inside it. And sometimes that is stipulated in A-level mark schemes that you must draw benzene with a circle inside it. I'm going to suggest that you actually draw one of the Kekulé structures for first year undergraduate level, because we're going to start using these double bonds in reaction mechanisms, and it's much clearer exactly where all the charges go if we're using a Kekulé structure. The reason you'll have been told to draw it like this is so that you understand that benzene is resonance stabilized. But at degree level, we take that as read. You understand that benzene is resonance stabilized. We're now going to use these resonance structures in actual mechanisms. So before we get onto any mechanisms, there's a really important rule to understand, and that's Huckel's rule of aromaticity. So there's various rules for defining if something is aromatic or not, but Huckel's rule is the most broadly applied, I think. So essentially, if a molecule is cyclic, it's planar, in other words, flat, and it has 4n+2 pi electrons in the ring, it's aromatic. That's Huckel's rule. So if we take benzene as an example, is it cyclic? Well, yes, it's a six-membered ring. Is it planar? If we look at the three-dimensional structure of benzene, we can see that it is indeed planar. It's made up of sp2 hybridized carbons, so they're all trigonal planar. It's a flat structure. Does it have 4n+2 pi electrons? Well, if we count them, 2, 4, 6, it has 6 pi electrons in total. 4 times 1 plus 2 equals 6. Okay, so if we take the equation 4n plus 2 and we substitute n as 1, then that gives us 6. So is it aromatic? Yes, it absolutely is. But we can apply this to any structure effectively. Let's take anthracene as an example. Is it cyclic? Yes, it is. It's made up of 3 rings fused together. Is it planar? Yes, it is. Does it have 4n+2 pi electrons? So we've got 2, 4, 6, 8, 10, 12, 14. 14 pi electrons total. 4 times 3 plus 2 equals 14. So it fits the equation. So therefore, it is aromatic. And just to give you one that doesn't work, cyclohexadiene, is it cyclic? Yes, it is. Is it planar? No, it isn't. We've got a saturated section of the molecule now. So this doesn't adopt a planar conformation. So we're off to a bad start. But does it have 4n+2 pi electrons? Well, it's got 4 pi electrons. That doesn't fit the formula. That is 4n rather than 4n+2. So therefore, it isn't aromatic. So this is a really useful way of just looking at first glance at a molecule. Is it aromatic or not? So reactivity. We've already said that aromatic molecules don't react the same way that alkenes do, right? If you take an alkene, like cyclohexene, and you treat it with bromine, for instance, it'll dibrominate. That's an addition reaction. If you take benzene and treat it with bromine, nothing will happen, okay? Because benzene is more stable, okay? So you need different conditions to force the reaction to happen, but you also get different products as well. So it's not just a case of adding a catalyst or something to force bromine to react with benzene. When you add a catalyst and force it to react with benzene, we only get one bromine attached and the double bond is still there. So this is a substitution reaction, not an addition reaction. Well, why does this happen? What we're getting here is called electrophilic aromatic substitution, and this is one of the core reactions that benzene and other aromatic molecules will do, okay? So I'm just going to use bromination as an example. We'll cover lots more examples in our sessions together. But in this case, we're having bromine and we're adding aluminium tribromide. You can also add aluminium trichloride, it doesn't really matter. But it's a Lewis acid catalyst. Okay, so aluminium has an empty p orbital on it, and you can use one of the lone pairs on bromine to attack that p orbital. And we end up with this sort of odd-looking charged structure here. Now, this has made bromine more electrophilic, and that means that the benzene ring is now more likely to attack it. So we're going to attack the bromine at the end, and we're going to kick the electrons onto the bromine in the middle, because the bromine in the middle is a hypervalent cation. We then end up with this intermediate. This is a cationic sort of benzenoid type intermediate. They're sometimes called Wieland intermediates, these things. And what you might be thinking now is, look, we've got an empty p orbital on carbon. We've got a hypervalent aluminium anion over here, which really wants to lose a bond and a pair of electrons. So why doesn't it just kick the bromine onto that atom there and give us our addition product? Well, that's what it would happen if it was behaving like an alkene. But aromaticity is an important thing. Aromaticity is an extra stabilization that you get from the molecule being aromatic. So rather than doing this, what it actually prefers to do is rip this proton off here. So bromine comes across, picks the proton off, and pushes the electrons from the carbon-hydrogen bond back over here to reform a carbon-carbon double bond, and that restores aromaticity. Okay, so that addition product that we saw wasn't aromatic because it only had 4 pi electrons. What this does, electrophilic aromatic substitution, is gets us back to an aromatic product, so therefore that stabilization is retained. So there's a whole range of different electrophilic aromatic substitution reactions. We've just seen halogenation. You can swap bromine for chlorine, Cl2, and that works just as well. But there's other reactions. Nitration is a really important one. This is how we make, essentially, this is how we attach nitrogen to benzene rings. So nitric acid and sulfuric acid is how you do that. And then there's 2 Friedel-Crafts reactions. So Friedel-Crafts alkylation is basically an alkyl halide with the same sort of Lewis acidic catalyst. And Friedel-Crafts acylation is an acyl halide or an acid halide with, again, the same catalyst. So we'll do lots of examples with these in our sessions together. One final thing I just want to talk about is directing effects. So if your aromatic ring already has a substituent on it, in other words, it's not just benzene, the substituents on the ring will direct where your electrophile adds to. So here's an example with phenol. Okay, we've now got this OH that's already attached to the benzene ring. If we brominate it, like we did with benzene before, there's 3 possible positions that it could attach at. Okay, you can go ortho to the hydroxyl group, you can go meta to the hydroxyl group, or you can go para. And you might expect, statistically speaking, that you'd end up with a 2 to 2 to 1 mixture because that's how many ortho, meta, and para positions you have. But actually, you don't. You end up with mostly ortho and para product, probably in this case more of the para, and you end up with very little of the meta product. Okay, then, we'll come on to why that is in a minute. But if we take nitrobenzene and we treat it with the same conditions, so exactly the same reaction conditions, okay, we've seen what happens with phenol. Surely the same thing happens with nitrobenzene then. We're going to end up with ortho and para product for some reason. No, we end up with pretty much exclusively meta product in this case. So what's happening here is that the substituent that's already on the benzene ring is directing where your electrophile attaches to. And let's see why. Okay, so first example, substituents with atoms that have got lone pairs on. And we're talking about lone pairs directly attached to the ring. So phenol's a good example, right? So amines and alcohols, where there is an atom containing a lone pair directly attached to the ring. Okay, so this could be OH or NH2 or whatever. What we can do in this molecule is we can draw resonance forms where we push that lone pair into the ring. And what you'll find is that the lone pair electron density ends up at very specific positions in the ring. And this is why I told you not to draw benzene as a with a circle in the middle, because it then becomes very vague about where things are. Okay, so the resonance form that we've just drawn puts the negative charge on this carbon, which is the ortho carbon to the oxygen. Okay, we can carry on because this is still conjugated. You can keep pushing it around the ring, but the carbon ortho to the hydroxyl group has now got more electron density. It's got a negative charge on it. Okay, more electron density makes it more nucleophilic. Bear that in mind. Continue pushing it around the ring. It ends up at the para position. So this resonance form has a para negative charge. The para position to OH has increased electron density, which makes it more nucleophilic. If we carry on around the ring, the other ortho position ends up with a negative charge as well. So all in all, our ortho, our para, and our other ortho positions are getting a share of the electron density from this electron donating OH group over here, and that's making them more nucleophilic. In other words, more likely to react with an electrophile. And that explains why the ortho and the para products are the major ones from this reaction, because we have a resonance electron donating group here pushing electron density into the ring, specifically to the ortho and the para positions. It skips over the meta position because that's not the way the ring's conjugated. So this is what we call an ortho-para directing group, anything that's conjugatively electron donating like this. There's another explanation in your workbooks, and that explanation is, some people prefer it. They prefer, to follow the structure of the intermediates in the reaction, but it also explains how inductively electron donating groups work. So alkyl groups are ortho-para directing, but obviously they don't have a lone pair. So go through the workbook to read about those ones. Opposite is true of electron withdrawing groups like nitro. So nitro groups and carbonyls that are directly attached to the ring are meta-directing. So for basically the same reason, we're going to draw resonance forms, but this time we're going to suck electron density out of the ring using this electron deficient NO bond up here. So we're going to pull electron density out like this, and that gives us a positively charged resonance form in the ring. So because we've got decreased electron density at the ortho position, that makes it less nucleophilic. So the ortho position is losing electron density, making it less reactive. And again, we're going to do the same thing. We're going to push that charge around the ring. It ends up at the para position. So the para position ends up less nucleophilic, and it ends up at the other ortho position over here, which makes that less nucleophilic. And then if we look at our distribution of our products from the bromination of nitrobenzene, the ortho and the para products are not formed as well, because those positions are less nucleophilic in the starting material. So we end up with the meta product. Again, there's an alternative explanation for this, dealing with the intermediates of the reaction, which you can go through in the workbook. It also explains how inductively electron withdrawing groups like CF3 are meta-directing. But there are some kind of niche examples. So halogens are the classic example. You might think that halogens are inductively electron withdrawing, but remember that they have lone pairs. So they have an ortho-para-directing effect as well. So hopefully that video was useful to you. We'll do lots and lots of problems based around aromatic chemistry in our sessions, and I'll see you there.